All right. So today I want to talk about the Pollaczek-Khinchine formula for the Mg1Q. And I want to derive it here. And I guess the first thing that to kind of tie this back into something more practical is, you know, why good VoIP calls can go bad. So, I guess the the highlight here is like, maybe you have had times where you've had like a VoIP call sound awful, even though the bandwidth looked fine. So, and usually this gets waved off as like just a network issue, and just move on. But in my research, I found that that answer hides the actual mechanism. So, and a lot of time, the problem is um, not raw bandwidth. Um, it's actually um, queuing. Um, queuing. I guess what I should say is instead of this is highlight. Oops, sorry. There we go. Um, is why good VoIP calls go bad. So this is um, a deep dive in a sliver of getting to the theory of why this phenomenon can happen. And so, I guess, I should say, like, let's just review here. Okay, the first thing that people say is what? Network issue. And it's just kind of, hand waved. Oops. It's just kind of hand waved. Okay, and maybe that's in the interest of time, maybe that's in the interest of practicality, maybe that's in the interest of many different factors. But you know, what what I'm interested in is getting down to the actual mechanism or one of the actual mechanisms. The actual mechanism. This is what we really want. Okay. So getting down to the actual mechanism. So, you know, um, so actual mechanisms, right? We can talk about it in maybe three different areas. One is queuing. The second is contention. And the third can be variance. Okay. So, now with that, if we just, you know, uh, go from this, the actual mechanism being one of these, or a combination, or all of these three things, we can derive um, the mathematics behind it. And there's a classic formula from queuing theory. Oops, from queuing theory. And I guess I should say I've studied the book performance modeling and design of computer systems by I think she's at Carnegie Mellon. Um, the researcher, Professor Dr. I believe it's Harkle Balter. She wrote this book, Performance Modeling and Design of Computer Systems. And this is where she goes into queuing theory and she brings up, um, and we'll talk about this, the MG1Q, the MG1Q. Okay. So let's go back to, we talked about these three different mechanisms that can make a good VoIP call go bad: queuing, contention, and variance. Now, there's a classic formula from queuing theory here, queuing theory, um, that helps us explain why delay and jitter can blow up. And the formula is called, I guess, the formula we care about and we'll be studying, and we'll be deriving, is um, Pollaczek, I believe that's how you say it, Pollaczek-Khinchine, I believe that's how you say it as well. I could be wrong. Either the way, two incredibly smart people came up with um, a formula to model um, um, the queuing process and the queue, in itself. And I'm just going back to my notes. Um, so, the one of the MG1Q, let's go back to this, the MG1Q, and I'll highlight. Khinchine. The MG1Q is, and we'll talk about this, is a Poisson process entering a queue. This is the queue. And there's customers. That's what we're encapsulating as the entities that are in the queue. And this is a first come, first serve queue. And run out a little bit of room here. And then there's the body of the service, right, which is mu, which is the general service time. This is the MG1Q, okay? So the Pollaczek-Khinchine formula, it explains why delay and jitter can blow up. So that's great, but the question everybody's asking is, why do I care? Or I should say, why should I care? Why should I care about this? Well, if you're in telecom, and voice over IP and dealing with communications, real-time communications, VoIP is the first kind of prerequisite of like why we should care is VoIP is fundamentally about um, stochastic, and we'll get into this, cues. in disguise. Oops. In disguise. What does that mean? Well, first, before we should do that, we should say, well, what is stochastic? What does that mean to be stochastic? And a system is stochastic um, if its behavior involves randomness. So the opposite of stochastic would be deterministic. So what does this mean, that it involves randomness? First, uh, you cannot predict the exact outcome. Only probabilities. Only probabilities. We're going to highlight this. Only probabilities um, of different outcomes. Okay. So VoIP inherently deals with stochastic cues, like jitter. We can, like jitter. Okay. This is a common, oh, sorry. A common thing we deal with in voice over IP, which, and we'll see here through the mathematics that it's essentially variance in service times. And that variance is inherently stochastic, right? So it's a purely stochastic phenomenon, the jitter. So let's go back. Oh, why should I care? VoIP is fundamentally about stochastic cues in disguise. And we know stochastic is about randomness, and you cannot predict the exact outcome, only probabilities of different outcomes, right? So let's move on. The other thing of, I guess, you know, uh, why should I learn this, about this formula? Why should I learn this? The Pollaczek-Khinchine formula. Why should I learn this? That's um, the main hallmark here is why should we learn this is, so like, first thing is like, in a VoIP call, the codec on each endpoint like G.711 or Opus um, produces audio frames at roughly a fixed rate. And we can say, like 50 packets per second. You can say that for an example. Now, ideally, the network would deliver these, and I guess I should say first, before to kind of make sure that this is clean. This is about RTP packets arriving over time. Right. So this is number one. This is the number one reason of why we should learn this, because RTP packets arriving over time, and so ideally the network would deliver these RTP packets at the same steady rhythm, but in reality, packets share links with other traffic. So packets share links with other traffic. That's one. And then they traverse routers with different loads. Traverse routers with different loads. Okay. And compete, like in 802.11 and Wi-Fi, compete for airtime. Okay. So hopefully I made that clear. So what does this mean? So the result. What does this mean? So the result is the send side is regular, but the arrival times at the receiver are irregular. And effectively random. So what does that mean? Like so we can say some packets bunch up, others are delayed. So queuing theory models this as packets arriving according to a random process at rate what we call rate lambda into an MG1 system. All right, well, that's great, but we need to go over, we need to review MG1. So let's just do it really quickly. For the MG1 queue, actually thinking about it, we can just keep it at this, that there's Poisson process, it's first come, first serve, like a normal queue, and then there's a general service time to deal with those customers. So we can just leave it at that because we'll get more into it later in the video. But so RTP packets arriving over time is one reason why we should care. The other reason, another reason why we should care is that the waiting in buffers happens in VoIP. So packets do not go straight from the network interface to the user's ear, right? So at each hop, they may wait in output queues on routers and switches. So say, waiting happens on routers and switches. then again in buffers like on the access link. So waiting at the access links, like fiber, LTE, etc. The different links, Wi-Fi also. And finally, waiting happens inside and the playout or a jitter buffer, waiting at the playout jitter buffer inside the IP phone or soft phone. So IP phone or soft phone. Okay. Okay. So let's stop here for a second. Okay. So waiting in buffers is another reason why we should learn this. Now, um, each of these is essentially a small queue uh, where packets line up and when they arrive faster than the link or device can process them. So the jitter buffer in particular, um, uh, like deliberately holds 20 to 200 milliseconds of audio so that late packets can still be, played out in order. So um, smoothing over the delay variation at the cost of added latency. So the Pollaczek-Khinchine formula, seen as the waiting in the queue, predicts on average how long packets must wait. Packets must wait because of current load, and the variability of service times. Okay, so this is why PK Pollaczek-Khinchine is important to us in the waiting in buffers reason. Um, there's also contending for service. There's a lot of there's contention for service. So like RTP packets contend with other traffic like web, video, backups, etc. for transmission over that finite capacity link. So when more packets arrive, um, when more packets arrive, then the interface um, when more packets arrive, then the interface can send. They get serialized and queued. And the service time is denoted as S. Let me rewrite this. The service time is denoted as S, which is um, the bits of the packets divided by, so the packet size divided by the capacity. Um, so, I mean, and this is the server in the MG1 model. Okay, so that's number 3. Number 4 is experiencing delay, jitter, and loss. So experiencing delay, jitter, and loss. So like end-to-end delay in a VoIP call is not a single number, but like a distribution with a mean and a tail. So, not a single number. And this really goes back to quality of service, not a single number, but a distribution with a mean and a tail, right? So if we think about, just like a like a normal distribution, right? Horrible drawing, right? But this would be tail, and then the mean would be here, right? So it's a distribution. It's a statistical distribution, right? And we know it models stochastic properties with randomness. And then, so uh, then let's bring this back to PK. Um, okay, and then, before jitter here um, is packet to packet variation in delay. Okay, so getting back to PK shows that the mean waiting time scales with the second moment. The second moment is this, and we'll see this in PK, and which is where like service time variance is mathematically enters the equation here. So what does this mean? So when variance or utilization, which is modeled as rho, are high, the tail, P95 and P99, explodes. And what is P95, P99? P95 is 95% of packets arrive faster than this value. Arrive faster than this value. And then P99 is same thing, but 99%. Okay. So when this variance or utilization rho, this value rho is high, the tail explodes, and then that is exactly what users perceive as choppy or delayed audio, right? So that's number 4. And number five is um, interaction with scheduling and congestion behavior. So, like quality service policies, priority queues, fair queuing, jitter buffer algorithms are all queuing disciplines that change how packets are scheduled on congested links, right? So, from a queuing theoretic point of view, these mechanisms uh, reshape arrivals and service to control. So, so understanding PK um, is really the formal language for reasoning about how VoIP packets experience quality of service attributes like delay, jitter, and loss. Attributes like delay, jitter, and loss. Okay? So those are the 5 reasons why we should learn this, and I want to bring it back to this first page. So, RTP packets arriving over time result in ultimately arrival times are irregular and random. Waiting and buffers are representative of small queues that build up over time, or I shouldn't say build up, but there's many small queues, and so and then contention for service happens, and then experiencing delay, jitter, and loss happens, and it's a probabilistic um, uh, phenomenon um, where jitter can happen, and then the interaction with scheduling and congestion behavior, where we can use PK, as a formal model to look at this. So, so when someone asks, let's do so. When someone asks, the bandwidth is high, so why does my call sound bad? We can answer um, that it could deal with uh, something queuing theoretic. So it could be, maybe burstiness is building queues, maybe serialization plus contention is spiking the delay, maybe jitter buffer interactions are masking a queuing problem, maybe utilization is too close to 1 during bursts, and we'll see that. And maybe the tail is killing quality even if the mean is okay. So the goal here is to build a mental map where we know like the major families of causes and can reason about the symptoms to mechanisms more rigorously than just we want to get away from, we want more uh, than just network issue being the reason why. We want to be able to answer more deeply why and more rigorously. So, so some prerequisites. So let's go over some prerequisites here. Prerequisites before we start PK. Before PK, um, there's the first moment of service distribution. The first moment of service distribution is this. And then the second moment, so I should say, I should just write it out. First moment. And this is taken from physics and just applied to statistics here. And then we have the second moment, which is the mean of the square. So we see these e's and we're going, well, what is that? So another prerequisite here is e is expected value. So meaning like the mean or the long run average of the random variable S. So then we have service time. What is service time? Is how long it takes the system um, to process one, customer, to process one uh, customer in the queue. So the unit of work, like one RTP packet, one RTP packet, right? Okay, and then we have utilization, which we saw earlier, which is rho, is the fraction of time the server is busy. So, how loaded the system is. Okay. So, and then knowing what a Poisson distribution is the probability distribution that models the number of random, I should redo this. Number of random independent events that occur on a fixed interval of time. When events happen at a constant average rate but unpredictable individual moments. Okay, so so and getting back to E, um, just something that I thought of. We can also say the value is the value you would converge to. You would converge to if you average thousands of observations. Um, okay. to further go into service time, just to highlight this, I mean, I know we're still in prerequisites here, but there's a lot of moving parts. So we have the packet size in bits, and then we have the capacity. And then, so therein, service time is defined as B P C divided by C, divided by the capacity. So packet size divided by the link capacity. So, okay, well then, you know, what is this link capacity? So link capacity is the maximum rate at which bits can be transmitted over a communication link. So it's you know, the speed of the pipe. So, and like for Wi-Fi, you know, it's like megabits per second. Data center or you know, fiber, you could have, you know, gigabits per second, right? So these are examples. So takeaway is, you know, bigger pipe, bigger pipe um, uh, leads to smaller S, so less weighting. Okay, and then utilization, if we go more deeply into utilization, rho, um, it's a number between 0 and 1, and the formula is lambda divided by mu. So where mu is the mean service rate, like you know, customers per second the server can handle. And then we have lambda, which is the Poisson arrival rate. Okay. So let's get right into PK now. So we've gotten the prerequisites out of the way. And feel free to go back in the video to review any of those if you feel shaky on it. But the PK formula now, and we can do this do it in blue, maybe, we'll see. Is this lambda multiplied by the second moment, 1 minus utilization, where the utilization is defined as lambda divided by mu, the mean service rate, and Poisson arrival rate. So S is, like we said, S is the service time. Um, the ES is the mean service rate. And so I should also say that this can also be written as the Poisson arrival rate times the mean service time. And then so we have the second moment of service time utilization, and this is the WQ is the waiting time in the queue. Okay, so and we're going to derive this. So PK formula. Okay. So, and then just from a mathematics standpoint, you know, let me see where to write it here. P, no, sorry, rho is less than 1. Okay. Um, so now let's get into system model. So we use the MG1Q, which M is Markovian, meaning arrivals like are modeled as a Poisson process with a rate lambda. G is general service time distribution. So this is Markovian. This is a general distribution, and one server. Okay. The server is the bottleneck resource. So serving packets one at a time. And this could be like a output interface, wireless medium, or like another transmission point. So an arriving job must wait for two things. So an arriving job must wait for, first thing is the remaining service time of the job currently in service. And then it should also wait for the service time of jobs already waiting in the queue. The service times of jobs already waiting in the queue. So therein, the waiting in the queue is defined as R plus queued work. So now we can do expected queued work. Queued work. And so let LQ be the average number of jobs waiting in the queue. So each requires that expected service time ES of queued work then is equal to LQ, sorry, Q given Okay. So using Little's law, we get the lambda uh, and Little's law states that in any stable queue, the average number of items waiting equals the arrival rate, lambda times the average time each item spends. Okay, so let me see here. So we have Little's law. So then E of queued work is equal to lambda waiting in the queue times. All right. Now we have utilization. Uh, find row. Row is equal to lambda that so the lambda times that arrival rate and the Poisson arrival rate times the mean service time. That's the utilization. So thus work waiting in the queue. Okay. And then we substitute into main equation in queue. And then we can see if we can rearrange this. Um, right, we can rearrange factor, or sorry, um, multiply both sides. 1 minus row, right? And then we can divide, right? So this is the expected queued work. Expected queued work. All right. Now let's do expected residual service time. Okay, so let S equal X be service time. So if an arrival occurs during the service, the remaining time is uniformly distributed 0 to X inclusive. So therein, we have E R given S equal to X is equal to X divided by 2. Okay. So however, like longer service times are more likely to be observed. So the observed distribution is length-based. So of the observed X equal to X F. So we get this. And then we can compute the expected residual time as, let me see here. Uh, Given busy equal to, oops, from 0 to infinity, x divided by 2 times x divided by x. Okay. So we can factor, yeah, we can factor this, and that turns into x squared dx. Okay, now, and so now we have that, and so we should say note for a continuous random variable s with PDF FSX, there is EGS equal to see GX FSX dx. And then if we choose, and then if g of x is equal to x squared, then we get um, squared x squared f s x dx. Okay, so if we have a note here about this fact that the second moment is equal to this value, then we know because this here is the same as this, right? So then we can say that then the next we can reduce this to e s. Okay. So then we can say the server is busy with probability rho. So then it becomes okay. So then we know also we know that rho is equal to lambda times the first moment. So then we can say to um, times the first moment times. Times second moment divided by 2. So first moment. And these cancel. So we're left with okay. And so let's see here. So we have our waiting time equation. Let's see. Right. Our waiting time equation is this. And so, and we found ER, which R is that the remaining service time of the job currently in the service. See if I can copy this. So we can plug this in equal to and, divided by. All right, and then we simplify it to right. And so the total time in the system is defined as waiting in the queue plus the first moment. So then we get is equal to, nice, yeah, plus minus row. Okay, so I think we did it. So what does this mean? I believe we did this. Let me see. Yeah. So this shows that one delay increases with rivalry random, or sorry, lambda. Delay also increases with variability at the second moment. And then also delay grows rapidly as rho approaches 1, right? Because it will explode. Okay. So utilization and service time variance critically impact queuing delay. So what does this mean? So utilization and service time variance impact queuing delay. Okay, so I think I derived it correctly. I could be wrong, but I came at the result. So, and I just tried to tie this back into voice over IP. Um, the MG1 queue, we didn't really go over that too much. Um, yeah, I mean, I think that's fine. So tied it back into voice over IP, and then why I learned this, and then we did the derivation of it. So I think that's good.